So we'll wait for a couple of minutes, then we can start. So we'll wait for a couple of minutes for other participants to join. If in case they didn't join, we can start. So I guess we have waited for, I think, more than 8 minutes. So none of the participants have joined. So anyways, we'll just start with our live lecture. And one more thing, people who are watching this live recording, I will try to be as thorough as possible because right now I don't have any feedback from the live audience. So I'll try to repeat every possible step. I will try to explain every possible step, and sometimes I will also repeat a question twice if I feel there's a need for that. So, so it's for your own convenience that I'll be going through things slowly. If you find this slow, you can always increase the playback speed, and that will be your that you can always play with. But this will be a very slow and detailed. It will go through at a very slow pace, and every possible step will be explained. Actually, my lecture was supposed to take place on Sunday, but I was traveling, so that this was postponed. And today I don't have any live audience. Anyways, we can start. And today we'll discuss stuff related to week 8. Sorry, there's some mess around here. So sorry for the delay. You guys can always skip this portion. So we'll start. So I don't think I need to share my screen as there is no one in the call. I can directly use the OBS recorder. Yeah. Anyways, if someone joins, I'll just share the screen then only. So I welcome you all to this live session 8 of the course Digital Circuits that is taught by Professor Shantanu Chattopadhyay. I'm your course TA. My name is Musab Rafiq. I'm a PhD student in the Department of Electrical Engineering at IIT Kanpur. Today, I'll be going through the questions related to week 8 material. In case of any doubts, you can always comment on the YouTube video, and I'll be more than happy to answer your doubts there. So, going forward to today's live session, we'll be discussing mostly questions related to mostly converters. Like we have analog to digital converters, digital to analog converters, and so on. So this live session will be focusing mostly on the data converters that are analog to digital converters and digital to analog converters. Actually, it's quite difficult to hold a live session without any live audience, but I'll try my best. In case you have any doubts, please let me know. If you want me to repeat any, I'm referring to the audience that are watching the YouTube videos. In case of any doubts, any queries, you can always comment on the video. So here's the first question of today's live session. It says that a 8-bit DAC has a step size of 25 millivolts. What will be the full-scale output voltage? So I'll just repeat the question. A 8-bit DAC, that is a digital to analog converter, has a step size of 25 millivolts. So the step size between each step is 25 millivolts. What will be the full-scale output voltage? So we need to find out the full-scale output voltage, that is the maximum possible output voltage that this 8-bit DAC will produce. So how will we approach it? We know this step size. So let me just write the step size. Step size is given as 25 millivolts. And in volts, it will be 25 by 1000, that is 0.025 volts. And I will call as the number of bit converter. That means the how many bit converter is this? How many bit output it will take as input? So it is an 8-bit DAC. So n is equal to 8. We know that step size is equal to full scale output voltage, full scale output voltage divided by 2 raised to power n minus 1. So that implies full scale output voltage. I'll just write it as FSO. FSO is equal to step size multiplied by 2 raised to power n minus 1. So what we did is we just simply wrote the formula for the step size, that is equal to full scale output voltage divided by 2 raised to power n minus 1. So full scale output voltage is equal to step size multiplied by 2 raised to power n minus 1. Now plugging these values that are given. So this is 0.025. I have kept it in SI units only. Multiplied by 2 raised to power 8 minus 1, that is 0.025 multiplied by 255, because 2 raised to power 8 is 266 minus 1 is 255, and this thing is equal to 0. Let me just check it. 0.025 multiplied by 255, it is equal to, this thing is equal to 6.375. 6.375. And one important thing, never forget the units. So this is equal to 6.375 volts. So option A is the correct answer. So this was question 1 of today's live session. Let me just check whether the NPTEL team has sent the communication to you guys. At least I anticipated a couple of students to join in. Let me just check whether you have. Okay, so someone is joined in. So thanks for joining. So I just showed one question to the audience, practically to no one. So do you want me to repeat that, or you will just refer to the live video recording? If you want me to repeat it, I can repeat it. Yeah, actually, there was no live audience, so I just showed one solution of one question. But if you want me to repeat it, I can just quickly recap that question. Yeah, yeah. So let me just share the screen first. Just a second. So are you able to see my screen? Okay. So the question one was, and we are given a 8-bit DAC that has a step size of 25 millivolt So we need to find the full scale output voltage. So the step size, I wrote it equal to 25 millivolt, and then I converted into the volts, that is 0.025 volts, and n is equal to 8, that is a 8-bit DAC. So we know that a step size is equal to full scale output voltage divided by 2 raised power n minus 1. So what I did then was I wrote this FSO, which is simply full scale output voltage equal to step size multiplied by 2 raised power n minus 1. So then it's equal to 0.025 multiplied by 2 raised power 8 minus 1. 2 raised power 8 minus 1 is 256 minus 1, that is 255, multiplied by 0.025, and that is 6.375 volt. So the full scale output voltage of a 8-bit DAC with a step size of 25 millivolt is 6.375 volt. That is option A. Now, towards the next question. So I had actually kept it for the audience. So just try it. It's an question states that an 8-bit DAC produces V out equal to 0.05 volt for a digital input of 0.00001. What is the full scale output voltage and the resolution of DAC respectively? So this question is along the lines of previous question, but slightly a different variation of that. So if we are using it 8-bit DAC and the output voltage is that is 5 millivolts, 50 millivolts in fact, 50 millivolts for one. What is the full scale output voltage and resolution of DAC? So if you can quickly try it, and then I will show you the solution. So did you try it? So in the previous question, we wrote this step size equal to full scale output voltage by 2 raised power n minus 1. So here the step size is simply zero point 0.5, 0.05 volt. Then it's the same. Let me just show you. So when we say this V out is equal to 0.05 volt for 0.00001, this simply means this is the step size, right? Because it's the first, that is the for one. For zero it had been zero, and then for one it will be the step size, because v of one minus v of zero will give you the step size, right? Then your what is this? This step size we know is equal to full scale output voltage by 2 raised to power n minus 1, right? That means that implies full scale output voltage, that is FSO in short, is equal to step size. I can call it as SS multiplied by 2 raised to power n minus 1. So your step size is 0.05 volts, and similarly it's an 8-bit DAC, so n is equal to 8. Let me just write it here, or n is equal to 8, so it will be 255. So 255 times 0.05 is 12.75. So it is 12.75. And one more thing, never forget the unit, so it's 12.75 volts. And also we need to figure out the resolution. So resolution will simply be equal to step size by full scale output voltage, that is FSO. So step size is given as 0.05 and your full scale output voltage is given by 12.75, and this thing will be equal to, let me just check what is this thing equal to. So this thing is equal to 0.00392, 0.00392, and in percentage by multiplying 100, so it is equal to 0.392%. So your resolution is this thing and your full scale output voltage is this thing. So it's 12.75 and 0.392%, right? So its step size multiplied by 2 raised to power n minus 1. So 2 raised to power n minus 1 will be the final value of an 8-bit DAC, right? 8, so what will be the last value of an 8-bit DAC? It will be 255, right? 0 to 255. So now we can go to question number, this was 2, right? Now we can go to question number 3. It states that if the resolution of a digital to analog converter is approximately 0.4% of its full scale range, then it is an, so we are giving the choices whether it's a 12-bit, 16-bit, 8-bit or 10-bit converter. We just need to figure out from the question what is the bit value of this converter. So we'll just start with resolution, because the resolution, that is what is given here. So resolution is given by full scale output voltage. So full scale output voltage, so I'll just call it FSO, by 2 raised to power n minus 1, as you saw in the previous questions. So this is resolution. So what is given is the resolution of a digital to analog converter is 0.4% of its full scale range. So this is equal to 0.4% of FSO. So that implies FSO by 2 raised to power n minus 1 is equal to 0.4%. We can write it like this: 0.4 by 100 times FSO, right? Simple mathematics. Then FSO and FSO will go away. That implies 2 raised to power n minus 1, sorry, not here. 2 raised to power n minus 1 is equal to 100 by 0.4, and this thing is equal to 100 divided by 4 is 25, so it will be 250, right? And that implies 2 raised to power n is equal to 251. So if you see 2 raised to power n, 2 raised to power 7 is equal to 128 and 2 raised to power 8 is equal to 256. So n, we can say, is equivalent to, I'm going to say, is equal, not equal to, approximately equal to 8. Actually it was log 2 of 251, but we need to find out the closest integer value, and the closest integer value is 8. So n is equal to 8, so it is an 8-bit converter. So what we did here is we were asked that a resolution of a DAC was 0.5% of its full scale range. So we just wrote the formula for this resolution, that is full scale output voltage by 2 raised to power n minus 1, that is equal to 0.4% of the FSO. So that means FSO by 2 raised to power n minus 1 is equal to 0.4 by 100 into FSO. So that's what we did. Just a second, I need to attend one call. Sorry about that. Sorry about it, please. Hello? I'm right now busy. Actually, I'm busy in lecture. We can talk later. Hello? So sorry about that. Actually, it was a call from my colleague. So was this question clear? Okay, just a second. I'll just text him. So this was question number 3. Now we can move forward to question number uh, 5, 4, I guess. Yeah. So question number 4 asks us, what is the output of the following circuit for the input B4 equal to 1, B3 equal to 0, B2 equal to 1, and B1 equal to 0. So before I proceed, can you just tell me what is this circuit? Yeah, am I audible? Yeah, that's right. So this is an R2R deck, and we are given with the digital inputs as B4 equal to 1, B3 equal to 0, B2 equal to 1, and B1 equal to 0, and the reference voltage is 16 volt. So it is an R2R deck, and we need to figure out the output of the following circuit. So here you can see the input pin is connected to this thing, that is the inverting terminal, and we know from the formula for us, let me just first write, this is an R2R deck. Formula from an R2R deck, that V out is equal to minus RF by R1, this is the gain factor for an inverting op amp, times VRF by BMSB. This is, I'm just writing a journal formula, BMSB by 2 raised power n plus BMSB minus 1 by 2 raised power 2 plus so on up to BLSB by 2 raised power n. Here it is a 4-bit deck, so we can write as minus RF by R1 times Vref. So your MSB is your B1, so it is B1 by 2 plus B2 by 4 plus B3 by 8 plus B4 by 16, right? Then I have RF and R are same, so it is minus RF by R, so it's R by R, so I can write it minus R by R. Pref is 16 as given in the question, and plugging the values of my digital inputs, so it's 1 by 4 plus 1 by 16, because the rest of them are 0, only 2 and 4 is 1. Then it's 16 times minus 16 times 4 plus 1, so this 16 and 16 will go away, so this thing is equal to minus 5 volts. Just the simple mathematics. The only catch was here, you need to figure out this was an R2R deck, and then you wrote the formula for this, that is minus RF by R1 times VRF, B1 by 2 plus B2 by 4 plus B3 by 8 plus B4 by 16. So any doubts in this question? next we have this question number. So next question is question number 5. So if you can try this question first and then I'll show the solution. So this question asks us an 8-bit DAC has a resolution of 20 millivolt per LSB. We need to find out the output voltage if the input is 10000. So you are given a 8-bit DAC having a resolution of 20 millivolt per LSB. Now we need to find out the output voltage if the input to DAC was 1 and zeros. That is 1 and 7 zeros. So you can try it, then I'll just show you the solution. So did you get an idea how to do it? Now let me show you. So what we have here is a resolution. This is the only thing that is available to us. So this resolution is 20 millivolt and that is 0.02 volts. Now you need to find out the digital this output of a DAC. So output of a DAC, that is V naught, is equal to resolution times the decimal equivalent of the digital input. Decimal equivalent. So this is 1, then how many zeros? 2, 3, 4, 5, 6, 7, 8. 3, 4. So this thing is equal to, if you do the conversion, this is equal to 2 raised power 7, that is 128, right? So your output voltage will be resolution, that is 0.02 multiplied by 128. So that is equal to 128 times 2, that is 256, and the decimal is after 2 digits, so that is 2.56 volts. So your output voltage is 2.56 volt, right? Is it clear now? Okay. So now towards this question, it asks us which of the resistance networks can be used as a 3-bit R2R ladder DAC. So assuming V0 corresponds to LSB. So can you just try it? Let's have a conversation regarding it. So can you just say which of these can be used as a R2R DAC? So see, whenever we talk about R2R DAC, keep in mind it needs to follow three conditions. Three conditions need to be satisfied for a network to be used as R2R DAC. Number one, the your digital inputs, that is here. So here we have three inputs, V0, V1 and V2. They need to be applied to the 2R resistor. That is the resistor 2R. They need to be applied to 2R resistor. So if you look at all three networks, they follow the criteria. So all three networks follow condition one. Three conditions need to be satisfied, all of them. Then it can be used as the R2R DAC. Number two condition is R, that is the resistance value with R, is in between. It is in between resistance 2R. So you have a resistor R and it's between the resistance 2R. So this thing follows, this thing doesn't follow. So here it doesn't follow. Sorry, this one doesn't follow. So this thing is not there. So network 2 does not follow. And this thing follows. So 1 is between 2 and 2, 1 is between 2 and 2. Now towards the third part, the 2R resistor, that is the final 2R resistor, is connected to ground. So you can see R is connected to ground, not 2R. So 1 doesn't follow. So the only network that follows all three criteria is network 3. So only network 3 can be used as a 3-bit R2R ladder DAC, right? So let me just repeat these three criteria. Number one, your digital inputs need to be connected to the 2R resistor. Number two, the resistance R is in between 2R. Number three, 2R is connected to the ground. So this is how you do it. Now, yeah, yeah, yeah. All three conditions need to be satisfied. All of them, all of them. Now, towards question number 7, it states that a 8-bit analog to digital converter is used over a span of 0 to 256 volt. So a 8-bit DAC is used over a span of 0 to 2.56 volt. The binary representation of 1 volt signal is, so then we need to find out the binary representation of the 1 volt signal. So how we approach it? Let's just find out the resolution. So the resolution is equal to V range by 2 raised power n. Then we have what is the V range? So the span on which it expands. So V range is equal to V high minus V low. So V high is your 2.56 and V low is your 0. So your range is 2.56 volt. That implies your resolution is equal to 2.56 by 2 raised power 8. That is equal to 2.56 by 256. So your resolution is equal to 0.01 volt, right? And your output voltage V naught is given by the resolution, as we saw earlier, resolution multiplied by the decimal equivalent. So that implies from this equation 1, decimal equivalent of the output. So it is equal to V naught by resolution. So V naught is your the voltage, that is 1, by resolution is 0.01. So 1 divided by 0.01 is simply 100. So the decimal equivalent is 100. Now you need to figure out the binary of 100. So the binary of 100 will be 251, 225, 1, sorry, 250, 0, 225, 0, 212, 1, 260, 230, 211. So it's it's 1, 1, 0, 0, 1, 0, 0. And for the 8 bits you can write 0. So it's 0, 1, 1, 1, 0, 0, 1, 0, 0. That is option 1. Now go towards question number 8. So the output voltage V naught of the circuit shown is, so we need to find out the output voltage of the following circuit. So let me just show the elaborate method. So we will just reduce this circuit. So this R and R, they are in series. So this will be 2R, and then this 2R and this 2R are in parallel. So it will be 2R in parallel with 2R. That is R, right? So this R plus R is 2R. Then this 2R is in parallel with this 2R. It's R. Then this R is in series with this R. So it's 2R. So my final network will then be equal to, wait, so this 2R, right? And then this 2R and 2R are again in parallel, so it will be R, and then this R and this R are in series, so it will be 2R. So my final network will be then equal to 2R grounded here, then 2R with input voltage V, and then this 2R, and then we have this thing connected to the inverting terminal of op amp, and we have this R. Let me just show it again. So this R and R are in series, this is 2R, then this 2R and 2R are in parallel, that is R. Then R and R are in series, so 2R again, 2R and 2R are in parallel again, so it means R. R and R are in series, so 2R, then the final network is this thing. Let's just call this node as Vx. So we can write from nodal analysis as Vx by 2R plus Vx minus V by 2R plus Vx by 2R equal to 0, right? That implies, so 2R as denominator and then transposing into the RHS, it becomes 0. So we have Vx plus Vx plus Vx. So we have 3Vx minus V is equal to 0, and then we have Vx is equal to V by 3. So this thing we got here. Now what we have here is this I that is flowing through this. So I is flowing through this and same I is flowing through this. So I is simply equal to Vx by R. How? Because this is virtual ground. So this thing here is 0. So Vx by 0 is 0, Vx. Vx minus 0 is Vx, and then Vx by 2R it will be your current. So I is equal to Vx by 2R, and I is equal to, plugging the value of Vx is V by 3. So we can write V by 3 times 2R. So I is simply equal to V by 6R, right? And then your output voltage, so V naught will be equal to minus IR. So minus IR, V out is equal to minus IR. So V naught is equal to I is your minus I is your V by 6R, and your R is R. So this thing and this thing will go. So your V naught will be equal to minus V by 6. So option C is your correct answer. Now towards question number 9. So I'd like you to do first, and then I'll show the solution. So it states that what is the output voltage of the circuit given below. There are two ways of doing it. One is a simpler way, just using the formula, and other you can use the elaborative circuit analysis. So whatever pleases you, you can try it. I'll give you, it will take 3 to 4 minutes. I'll give you 3 to 4 minutes. Till then I'll have a short break. Once I come back, I'll just show you the solution. So have you done it? Okay, no worries. Let me just show the solution. So this is again an R2R DAC with this thing connected to the R2R ladder connected to your non-inverting terminal. So let's just term it as VZ. So your VZ will be equal to, directly from the formula, Vref by B1 by 2 plus, where B1 is your MSB, B2 by 4 plus B3 by 8 and B4 by 16. So from question, this B3 is equal to 1 and all other are equal to 0. So it's Vref by times 1 by 8, and then this Vz is equal to, let me just, actually my mouse is slipping. So Vz is equal to Vref. So your Vref is 1, I guess. So 1 volt. No, not 1 volt. How much is Vref? Vref. Vref by 8. Vref is 1 volt, I think. Yeah. So it's 1 by 8. Then your V out. So here this V out. So V out will then be equal to, for an non-inverting case, your gain is equal to 1 by Rf plus R1. So it is 1 by Rf by R1 times Vz. So your output will be equal to V out is equal to 1 plus, so your Rf is 7 and your R1 is 1. 1 by 7 by 1 by 8. So it's 8 times 1 by 8, that is equal to 1 volt. There's other way of doing it, because sometimes when you are appearing in competitive exams, you don't remember whether there's a shortcut to do it. So you just use the circuit analysis. So what you will do here is, this 2R and 2R are in parallel, right? They are in parallel. So 2R and 2R will reduce to R, and then this R is in series with R, so it is 2R. So your final circuit will then be equal to 2R, then this 2R, which is connected to 1 volt, then you have R, then you have 2R, then you have R, and then you have 2R. And this thing we termed it as VZ. So this is 2R, this is R, and this is R. Let's just write for this node as Vx and this node as Vy. So let's do nodal analysis first at node X. So Vx by 2R plus Vx minus 1 by 2R. So Vx minus 1 by 2R plus Vx minus Vy by R is equal to 0. That implies Vx plus Vx minus 1 plus 2 times Vx minus Vy. This 2 we got from this denominator, because we are taking 2R as a common denominator, is equal to 0. And if you reduce this thing, it will be equal to Vx is equal to, I'm just writing in short, Vx is equal to 2 Vy plus 1 by 4. So this is your equation 1. Now let's do the nodal analysis at y. So we have Vy minus Vx by R plus Vy by 2R plus Vy minus Vz by R equal to 0. Then again taking 2R as denominator and then transporting it to the right side. So we have 2V, we have, I'm just skipping some steps. So 5Vy minus 2V, this is simple mathematics, it's not that difficult. 2Vz equal to 0. And now using this value here, my final expression for Vy will be equal to 1 plus 4Vz. So this thing here, this is not Vref. Ignore this. This is not Vref. Yeah. So Vy is equal to 1 plus 4Vz by 8. Now we'll do the nodal analysis at node Z. So Vz minus Vy by R plus Vz by 2R is equal to 0. That implies 3Vz is equal to 2Vy. And then plugging this value, we get Vz is equal to, we get 3Vz, we got Vz equal to 1 by 8. So once you solve it, you get Vz equal to 1 by 8. And then your V out will be equal to 1 plus Rf by R1 times Vz. And that thing is equal to 1 volt. 1 by 8 times 8, that is equal to 1 volt. As you can see here, V out is equal to 1 plus Rf by R1 times Vz. Your Vz was 1 by 8, so this thing is equal to 1 plus Rf by R1 times Vz. Vz is 1 by 8. Any doubts here? Yeah. So this thing I got confused. This was not Vref, this was simply the Vz voltage that you need to figure out. And this thing was simply the nodal analysis. This is this is pretty simple using the nodal analysis, circuit analysis, and this was directly using the formula. Now we have this question. This is what should I call it as ADC. Find the binary output voltage for the input voltage Vin equal to 4 volt and the V reference is 6 volt. So you need to figure out the digital output for this ADC with V in equal to 4 volt and V ref equal to 6 volt. So let's just term these voltages as V1, V2, V3, V4, V5, V6 and V7. So your V1, this thing is equal to, if you use this voltage divider rule, this V1 is equal to V ref by 8. Simply this is equal to V ref by 8 because this is total 8R multiplied by R. So V ref by 8R times R, so that is V ref by 8. Then your V2 is equal to twice V ref by 8. Your V3 is equal to thrice V ref by 8. Your V4 is equal to 4 times V ref by 8. Your 5 is equal to 5 times V ref by 8, and so on up to V6. Let me just write it. Only two voltages need to be written. V6 is equal to V6 times V ref by 8, and your V7 is equal to 7 times V ref by 8. Now evaluating this V7, that is this voltage. So this is 7 times V ref. How much is V ref? 6 by 8. So this is equal to 42 by 8, that is 5.25 volt. So 5.25 volt is greater than 4 volt. So this output of this comparator will be 0. So 6 times 6 by 8, that is 36 by 8, that is 4.5. So 4.5 is again greater than 4 volt. So we are comparing with the V in voltages, right? So this thing is 0. Then we have 5 times V ref by 8, that is 6 by 8. So 30 by 8, that is 3.25 volt. So this thing is 1. So this thing is 1. That means my output will be equal to the binary equivalent of 5. So binary equivalent of 5 is 101. So this thing is equal to 101. So they all will be equal to 1, but I'm not concerned about them because I know they'll all be equal to 1 because my v4, v3, v2 will all be less than vin. But once I found out the value of d5 equal to 1, I stopped it because I'm using the priority encoder. So once d5 is equal to 1, I don't care about d4 and all. So my output will be equal to 101. So option B is the right answer. Did you get this? So now question number 11. So this was 10, yeah. So question number 11, can you just solve it? What is the resolution of a 8-bit DAC AD converter which has a full scale analog input of 5 volt? Can you just find it? So your range of input is 5 volt and the number of bits it is 8. Right. Yeah, that's correct. So how we do it? So we have this 8-bit DAC having a full scale output input of 5 volts. So we'll just write the resolution is equal to V range by 2 raised to power n. So my V range is 5 by 2 raised to power n, n is 8. So 5 by 2, 5, 8. So this thing is equal to 0. Approximately equal to 0.019 volts. And if you convert it into millivolts, so it's 19 millivolts. Option A, as you rightly said, is the correct answer. Now again, you have a question. Size of a priority encoder required for a 3-bit flash ADC is. So can you just tell me what will be the size of a 3-bit ADC flash and priority encoder required for a 3-bit flash ADC? No, 3-bit, 3-bit. If you just simply, so yeah, you just saw it here only, right? This was nothing but a flash ADC 8 cross 3 encoder that is required, 3-bit flash ADC and having 8 inputs and 3 outputs, right? So option C is your right answer. So let me just draw here. So 8 inputs and 3 outputs. And how many comparators will be required? 7. So here you have it, 7. Now we have a question. It states that maximum conversion time of a 8-bit successive approximation ADC for a 2 MHz clock frequency is. So we have this formula for this successive approximation ADC. Conversion time is equal to n times frequency of the n times time of the clock. So n is your 8, n is 8, and time of the clock is 1 by f. So that is 1 by 2 into 10 to power 6. So it's 4 into 10 to power minus 6. So it's 4 microsecond. So the maximum conversion time for 8-bit successive approximation ADC is 4 microsecond. Now we have question number 14. It states that a 4-bit R2R DAC using inverting op-amp as a reference of 5 volt as a reference of 5 volt. What is the analog output for the input code 1010? So we have 1010 as a digital input. So your B1 is equal to 1, B2 is equal to 0, B3 is equal to 0, and B4 is equal to 0. And it is converting to the inverting op-amp. So we know that inverting terminal of the op-amp. So we know that V output is equal to gain of the op-amp, that is minus RF by R1, because it's converting to inverting op-amp, times B1 by 2 plus B2 by 4 plus B3 by 8 plus B4 by 16. So plugging these values, so here we are not given this value of RF and R1, so I am assuming RF is equal to R1. So this thing will be equal to 1. So minus 1 times B1 by 2 plus 0 plus 1 by 8 plus 0. So this thing is equal to minus times, and also we have this Vref here. So it's 1 by 2. So it's 1 by 2 by 1 by 8. So taking 8 as denominator, so it's 4 plus 1 by 8. So it's minus Vref by 8 times 5. So it's minus Vref is your 5 minus 5 multiplied by 5 by 8. So it's 25 minus 25 by 8. That is minus 3.125 volt. So option 3 is your right answer. Now towards question number 15. So I would like you to try it first, and then I will show the solution. So it states that a 10-bit DAC digital to analog converter is calibrated over a full range of 0 to 10 volt. If the input of the DAC converter is 13A, so 13A in hex, then the output rounded off to 3 decimal places is, so you are given a 10-bit DAC and you are given the full scale output voltage, that is range of the full scale output. You need to figure out the input, I need to figure out the output of the DAC if the input of the DAC is 13A, that is in hexadecimal system. So just try it. It's simple. You have tried these types of questions in the past, so you'll be able to do it. So have you tried it? Mm-hmm. Yes. Yeah. So you are very close to the answer. Yeah. Your approach is correct. So let me just show the solution. So it is a DAC ADC. So it is a DAC converter. So your output voltage is simply equal to the resolution times the decimal equivalent, right? This much you have figured it out. So this is the main part of this question. Other rest is pretty simple. So your resolution, so since it is a DAC, so your resolution is equal to full scale output voltage as we did in the earlier questions by 2 raised to power n minus 1. So your full scale output voltage is 10 by 2 raised to power 10 minus 1. So why 10? So this is n is equal to 10. So it is 10 by 2 raised to power 10 is 1024 and 1024 minus 1. So it's 10 by 1023. Right, keep it like this. And then your decimal equivalent of 13a. So this thing in decimal equivalent is, so this is 16 square simply plus 16 into 3 and a is 10, right? So this is equal to 256 plus 16 into 3, 32 plus 16, that is 48 plus 10. So it's 256 plus 58, that is 256 plus 58, that is 314. So your decimal equivalent is 314. So your output is simply equal to 314 multiplied by 10 by 1023. So this thing is equal to approximately equal to, rounded up to 3 decimal places, 3.069 volts. So your answer is, where it is, 3.069. So you were on the right path. You would have gotten the answer. So your next question is, how many comparators are required for a 3-bit flash type ADC? So how many comparators are required? You just saw it. Yeah, yeah. So 7 are required, and in general we can write for n-bit flash ADC we will require 2 raised to power n minus 1 comparators. So here n was 3, so it's 2 raised to power 8 minus 1, that is equal, sorry, 2 raised to power 3 minus 1, so it's 8 minus 1, that is equal to 7. Now towards the last question of today's, yeah, it's the last question. So I would like you to try it first, then I will just show the solution. So find the binary output produced for the input voltage Vin equal to 10.13 volt and Vref equal to 16 volt. We just saw one question along these lines. You can try it and then I will show the solution. Yeah. So in that question also we got 101, right? So this is a coincidence. Both of them got a answer of 101. So let me just show the solution. So what we have here is, so we have this thing, a flash ADC. So let's just call these voltage that V1, V2, V3, and this as V7. So your V7, as we saw earlier, is equal to 7 times Vref by 8. So your V6 is equal to 6 times Vref by 8. Your V5 is equal to 5 times Vref by 7. Sorry, what I am doing? Yeah, Vref by 8. So your V4 is equal to 4 times Vref by 8, and so on up to V1 is equal to Vref by 8. So this is equal to 7 multiplied by Vref is equal to 16 by 8. So this is equal to 14 volts. This thing equal to 6 times 16 by 8, so 12 volts. So this thing is equal to 5 times 16 by 8, that is equal to 10 volts, and this will be equal to 8 volts, 4 volts, so on. So we have V in equal to 10.13 volts. So this thing is greater than 10.13 volt, this thing is also greater than 10.32 volt, and this thing is less than 10.13 volts. So D5 will be 1, so that means my output will be 101. That is a binary equivalent of 5. So 101, as rightly said, is the correct answer. So any doubts in the live session? So that is a notation. You can always use any notation. That's I have just taken that thing. That's not. I have just taken V7 at the top just for this matching those comparator terms. That's a notation. That's nothing to do with this anything else, because that is an input to D7. That's why I wrote it V7. So any other doubts in the live session? So if there are no doubts, so how much time we have spent on the live session? So any other doubts? So let me just quickly show the questions I have solved. So this was the first question, just simply using the formula and you can get the full scale output voltage. And this was also based on this thing, but here you are given the output voltage for corresponding to digital input 1. So from that you got the step side and then you just approach the question. This was again based on this thing where resolution was given in terms of the percentage of the full scale output voltage, and using the formulas you got this. You need to figure out what type of converter this was. So it was an 8-bit converter. Again, this was a R2R ladder DAC where you use the formula and you got the output voltage. This was again this 8-bit DAC and simple question, nothing new. This was a case where three networks are given and you need to figure out which one could be used for R2R DAC. So here I showed that three conditions need to be satisfied to be used as the R2R DAC, where condition 1 was all inputs need to be applied to the 2R resistor. Condition 2 is that R resistor should be in between 2R resistors, and in the condition 3 that the last 2R resistors should be the grounded. Only network 3 followed all three criteria, and thus only network 3 can be used in the R2R ladder DAC. So this was again a question based on the converter where a full scale output voltage was given and you just needed to figure out what will be the digital output for the binary representation of 1 volt. This was a question based on the R2R DAC. Here I showed using circuit analysis how you can get the output voltage. This was also based on this R2R DAC where I showed that two ways of solving it. One was directly using this formula, and here the input were this R2R DAC ladder was connected to the non-inverting terminal of the op amp, and also this other way was the circuit analysis. Using that you could easily get the solution as well. This was a 3-bit ADC, flash ADC, where the input voltage was 4 volt and reference was 6 volt. And using the formula, that is V1 equal to Vref by 8 and all, you can just solve it. And here V5 was less than V in, so D5 was 1, and as a result your output was 101. This was a simple numerical question where a 8-bit DAC ADC converter had a full scale input voltage of 5 volt. You need to find out its resolution. Then this was a simple theoretical question which asks us the size of the priority encoder required for a 3-bit flash ADC. That is simply this thing, and you can see that the priority encoder required is 8 cross 3. And also then we had a question on successive approximation ADC where the conversion time, we need to find the conversion time having a clock frequency of 2 megahertz. So the conversion time was equal to n times time of the clock. So it is 8 by 1 by f, so that is 8 by 1 by 2 into 10 to the power 6. So it's 4 into 10 to the power minus 6, that is 4 microsecond. This was again a question based on R2R DAC, where input was connected using inverting op amp as a reference for 5 volt. This was a question where we had a 10-bit DAC converter that calibrated over a full range from 0 to 10 volt, and the input was 13 AHz, and we need to find the output voltage. Here we had this simple question. We need to figure out how many comparators were required for a 3-bit flash ADC. In general, for an n-bit flash ADC, 2 raised power n minus 1 comparators are required. And then this was again a question based on 3-bit flash ADC. We were given this input voltage of 10.13 volt and a V reference of 16 volt, and we found that again at voltage at comparator D5, we got input as 1, and as a result the priority encoder gave the output as 101. So if there are any doubts, you can comment on my YouTube video that I'm going to upload after this session. And other than that, we will meet next week at Sunday 3 to 5 p.m. That is our usual time schedule. Last week and this week, due to some personal engagements, I got my lecture postponed. But next week, hopefully I will definitely be available on 3 to 5 p.m. That is our usual time slot. So next week we'll meet at 3 to 5 p.m. So thanks for joining. If there are any doubts, you can always comment on the recorded video. Yeah, yeah. So yeah, 2 to the power n and 2 to the power n minus 1. Actually, I also had the same doubt, but I think I'm using 2 raised to power n minus 1 in DAC and 2 raised to power n in ADCs. So I think that's the difference, because I was also getting confused because the actually I have to follow certain answer key that I am made available to me, and according to that it was 2 raised to power n in DAC and 2 raised to power n minus 1 in ADC. You can also check it. I tried looking up at these thing, but I couldn't get a clear cut answer for this. Maybe I need to just see it again. But as far as I've seen, maybe I'm not sure. This may be an incorrect explanation, but just you can just check it and even refer to the lecture notes, because the key was made available by the NPTEL team. And in fact, in last year, while I was giving this lecture, I also saw it. Maybe there will be some explanation. Maybe I'm not aware of that right now. So once I have it, I'll just update to you. So someone has asked you whether it will upload in YouTube. Yeah, all the lectures are uploaded on YouTube, and they are the link is made available to you in the NPTEL. This what should I call this NPTEL portal of the SWAYAM portal. The link is there only. So thank you guys for joining. If there are still any doubts, you can always comment on the live recorded videos, or even in the next live session, you can ask me. No worries. Okay, thank you.